Constructive interference occurs when two wafers which are in phase superposition with each other. Now let's see this example. These two wafers are in phase. For example, at this point the phase is 90 degree, and this point the phase is also 90 degree. So at the same points the phase is the same. So therefore we say these two phases are in phase. In phase means that the phase is the same. Okay, and let's say the amplitude is 2 cm, and this one the amplitude is 2 cm, and when these two wafers superposition with each other, it will produce a wave with amplitude 4 cm. So from here we can see that if two wafers which are in phase superposition with each other, they will produce a wave which oscillate with a very high amplitude, and we call this constructive interference. So in conclusions, if two wafers are in phase and their superposition with each other, the resultant wave will oscillate with maximum amplitude, and this is called the constructive interference. Then how about destructive interference? Destructive interference occurs when two wafers are antiphase superposition with each other. Now let's see this example. These two wafers are antiphase. Now how do we know it's antiphase? For wave 1 at this point, what's the phase? We have learned this before. So the phase at the crest here is 90 degree. And for wave 2, the phase at the trough here is 270 degree. Okay, so the phase difference between these two wafers are 180 degrees. 270 minus 90, we get 180 degree. And if the phase difference is 180 degree, then we say these two wafers are antiphase. Okay, so these two wafers are antiphase. And let's say the amplitude for phase 1 is 2 cm and phase 2 will be negative 2 cm. Okay, and if these two wafers superposition with each other, the amplitude of the resultant wave will be 0. Okay, 2 plus negative 2. Okay, we get 0. And the same things occurs at any other points. Okay, so here the amplitude is 0. And if this point superposition with this point, the amplitude is still 0. And this point with this point, the amplitude is 0. So we can see that if two wafers are antiphase superposition with each other, it will produce a wave with 0 amplitude or very, very low amplitude. Okay, so in conclusions, two wafers are antiphase. If they superposition with each other, they will produce a wave oscillate with minimum amplitude or very, very low amplitudes, and this is called destructive interference. Okay, now let's use the Java applets that we discussed just now to investigate the constructive and destructive interference. Okay, now this time I would like you to set the parameters of the wave to continuous. Just now it's pulse, so I want you to set it to continuous. Okay, now for the amplitudes, you can put it equal or unequals. Okay, and the phase, you can put it in phase or out of phase. Okay, let's put it in phase. Okay, now let's see what will happen when two wafers superposition with each other. Okay, now from the applets, we can see that when two wafers superposition with each others, there is a place where the wave oscillate with a very, very high amplitude. For example, at this place, the wave oscillate with a very high amplitude, and also at this place, the wave oscillate with very high amplitude, and also at this place, the wave oscillate with very high amplitude. Now let's see this again. Okay, so we can see that here, okay, maximum amplitude, here maximum amplitude, and here maximum amplitude. So this is a constructive interference. And we can also see that there are points where the wave oscillates with 0 amplitude. For example, at these points, we can see that there is no oscillations at all, right? Okay, so this is the place where destructive interference occurs. Okay, and this point also destructive. This is a place where destructive interference occurs. So constructive interference is interference where the wave oscillates with maximum amplitude, and destructive interference is the interference where the wave oscillates with the minimum amplitude. Okay, there are a few parameters that you can set for this wave. The wave patterns produced by these two sources. Now, these are two sources with one frequency, means that the frequency of the two sources are the same. And if you still remember, waves with the same frequency are coherent wave, which means these two sources are coherent. So let's uncheck to see the wave patterns produced. Okay, so this is a wave pattern producer, okay, and we call these the interference patterns. The wave produced by the two sources interfere with each other and produce these patterns, okay, and from here we can see that there are places where the wave oscillates with a very high amplitude. There are also places where the wave only oscillates with a minimum or zero amplitudes. And just now we have learned that the place where the wave oscillates with the maximum amplitude is called the antinode, and the place where the wave oscillates with the minimum amplitudes or zero amplitude is called the node. So this is how the interference patterns look like. So just now we have seen the interference patterns from the physics simulations applets. Now in this slide we're going to see how these interference patterns occurs and how to identify the nodal and antinodal lines. From this image, we can see that there are two sources, S1 and S2, and these are the wave produced by source 1, and these are the wave produced by source 2. And the key here shows that the solid line is the trough. Okay, if you still remember, the trough is the bottoms of the wave, and then the dashed line represents the crest. The crest is the peak of the wave. Okay, and then the circle represent the node. Okay, we haven't drawn the node yet. Okay, so you can't see the circle and the dot yet. So the dot represents the antinode. Okay. Now, what I want you to do is to identify the node and antinode from this image. For examples, let's see. Okay, so let's look at this point. Okay, so this is a trough and this is the crest. And we have learned that when a crest superposition with a trough, a destructive interference occurs and the product is a node, okay, where the amplitude equal to 0. So therefore, this is a node because a trough interfere or superposition with a trough. So we have a node here, and here there's another trough and crest, so we have another node here. So I would like you to identify all the node, okay, to identify all the node, okay, and also I would like you to identify all the antinode. For example, this is the point where a trough superposition with another trough, and we have learned that if a trough superposition with another trough, constructive interference occurs and the product is a trough with a bigger amplitude. So this is an antinode, okay? Now this point, at this point, the crest superposition with another crest, okay, and we have learned that if there is a crest superposition with another crest and constructive interference occurs and the product is a bigger crest with higher amplitude, therefore this is also another antinode, okay? So let's mark all this antinode here, okay? Okay, now this is the nodes and antinodes, nodes, antinodes that we can find in this diagram, okay? Now if we draw a line to connect all the nodes together, okay? This is another one, okay? And here is another one. Okay, so the lines that connects all the nodes together is called the nodal line. Okay, so these are the nodal lines. Okay, and if we draw a line to connect all the antinodes together, okay, so this is a line to connect all the antinodes together. Okay, so the lines that connects all the antinodes together is called the antinodal lines. Okay, so this is a nodal lines and antinodal lines from interference patterns. And for the interference patterns produced by the physics simulations applet, we can see that this is the antinodal lines. This is antinodal lines. This is the antinodal lines. Okay, so this is the antinodal lines. Okay, antinode is the place where the wave oscillates with maximum amplitude. Okay, and for the place where the wave oscillates with zero amplitude, okay, this is the node, and the lines that join all the nodes are the nodal lines. So these are the nodal line. Okay, and these are the antinodal lines. Formula of interference. The interference patterns can be used to find the wavelength of the coherent wave. Now let's see these examples. There are two sources here, and the wave produced by the two sources interfere with each other and produces interference pattern here. And let's say the solid lines here represent the antinode. Okay, the distance between the two sources is denoted by the symbol A. And then the distance between two successive antinodal lines is represented by the symbol X. And the distance from the source to X is denoted by D. Then the wavelengths of these two coherent waves can be calculated by using the formula lambda equals to AX over D, where lambda is the wavelength and A is the distance between the two sources, X is the distance between two successive antinodal lines, and D is the distance from the source to X. X is where we measure the distance between the successive antinodal lines. So this is a very useful formula for us to find the wavelength of a wave, especially to find the wavelength of sound wave and the wavelength of light wave. We are going to discuss interference of sound wave and light wave in next lesson. Example 1. Two round dippers separated by a distance of 6.0 cm is connected to a vibrator to produce two coherent sources of spherical waves. So the round dippers are the source of the wave, and just now we learned that the distance between the sources of the wave is denoted by the symbol A. So A is equal to 6.0 cm. The distance between the sources and where X is measured is 20.0 cm. Just now we learned that the distance between the source and where X is measured is denoted by the symbol D. Okay, so therefore D is equal to 20.0 cm. 20.0 cm. Okay. If the distance between two successive antinode line is 3.0 cm, distance between two successive antinode line is given by the symbol X. So X is equal to 3.0 cm. So A, determine the wavelength for the spherical wave. Okay, so wavelength is lambda. Lambda equals to what? Okay, so let's use the formula for interference. Lambda equals to AX over D. Substitute all these values into this formula. A equal to 6, X equal to 3, and then D equal to 20. So the answer is 0.9 cm. So the wavelength is equal to 0.9 cm. B. if the separations of the two sources is increased to 8.0 cm. Now just now, the distance between the two sources is 6.0 cm. Okay, now it is increased to 8.0 cm. D remain the same, 20.0. Okay, and lambda is equal to 0.9 cm. Okay, so in this case we want to find x, okay, because they want us to find the distance between two consecutive antinodes, that is x. So this is for B. This again we use the same formula, lambda equal to ax over d, and a equal to 8, x we don't know, and d 20, and lambda equal to 0.9. Okay, then by using your calculators you should get the answer x equal to 2.25 cm. Okay, the distance between two consecutive antinodes is equal to 2.25 cm.